So in the previous videos, we saw how entropy generation happens and how that change in entropy of a system can be negative, 0 or positive, but the entropy generation has to be either 0 or positive and it cannot be negative. That is to say that the entropy of an isolated system either remains constant or continues to increase, and if we assume the universe to be an isolated system, which until our experience right now seems reasonable, then we can conclude that the entropy of the universe is continuously increasing. In this video, we are going to take a look at some key points about entropy, some things to note about entropy and remember, because we will from now we will continue to use entropy for the rest of our course in thermodynamics, as well as you will continue to use entropy for your future courses as well as your work in the future. So some things to remember about entropy. So I'll call that notes on entropy. Right. The first thing that we learned is that processes can only occur or happen in one direction, right? And that even though a process may obey the first law of thermodynamics, if it does not result in an increase in entropy of the universe or the isolated system in which the system is contained, then that process cannot take place, right? And so processes can only occur in one direction, and what direction is that? That direction is the direction of increasing entropy, right? So So note that this is the entropy of the universe that needs to increase, and it is not necessary that the entropy of the system increases. So in fact, when we remove heat from a system, for example, the entropy of that system is likely to decrease, right? So the system can have an entropy decrease. There is absolutely no problem with that, except that the universe cannot have a negative entropy change. That is, the entropy change in the universe is either 0 or positive for any possible process for it to be possible, right? So that is, processes can only occur in certain directions. The second thing that we note about entropy is that entropy is a system property, or what we call a state function or a state variable. Despite all the discussion about reversible and irreversible processes and the association of the generation of entropy with irreversible processes, it is sometimes hard to believe that entropy is actually a state function or a state variable, and that its value depends only on the state of that substance or of that system, right? And so therefore, it does not depend on how you got to that state. The entropy only depends on what that state is, and so therefore it's a state variable or a state function, and that the extensive variable is just entropy with units of joule per Kelvin, and the corresponding intensive property is small s, which is equal to capital S per unit mass. So that is with the units obviously joule per kg Kelvin, right? And so entropy is a state variable or a state function, right? And the other important aspect of entropy is that entropy is not a conserved quantity. And this might be one of the most counterintuitive aspects of entropy, because on the one hand we say that it is a state variable, it's a state function. On the other hand, we say that entropy is not a conserved property, and that I don't need to have entropy before a process and after a process to be equal. And these two are somehow counterintuitive, that these two can be true about entropy at the same time, but they are. And that entropy is not a conserved variable. But this is not a surprise. Many of the variables that we have worked with so far are in fact not conserved variables. For example, internal energy is not a conserved variable, right? Enthalpy is not a conserved variable. Energy of the universe is a conserved variable, right? But not internal energy of a system, for example, is not conserved. Enthalpy of a system is not conserved. Temperature or pressure of a system is not conserved. So we have worked with many variables or many properties of systems that are not conserved, and entropy just happens to be another one of those systems that are not conserved, right? So I don't need to have entropy of the universe at the beginning of a process or at the end of the process. I don't need them to be equal. In fact, a test of whether a process can actually take place or not is whether the final entropy of the universe is greater than or equal to the initial entropy, and that it can never be less than the initial entropy, right? So entropy final of the universe is greater than or equal to entropy initial of the universe, right? So it is not a conserved variable or a conserved quantity, right? And finally, entropy Unfortunately, however, entropy generation corresponds to irreversibilities in the system, and as we know, reversible heat engines, reversible heat pumps, reversible refrigerators have maximum efficiency when they operate in a reversible manner, right? And that irreversible engines will never have an efficiency that is as high as a reversible engine operating between the same two temperature reservoirs. Similarly, an irreversible heat pump or a refrigerator is never going to have the same as COP or even a higher COP as compared to a reversible heat pump or a refrigerator, again operating between the same two temperature reservoirs. And so therefore, irreversibilities are a measure of degradation of performance. In other words, irreversibilities degrade the performance of engineering devices, and irreversibilities can be measured or quantified with this entropy generation term, that is Sgen. And Sgen tells you how much entropy is generated within an engineering device or a system, and that corresponds to the irreversibilities present in the system. And so if we wanted to improve the performance of a certain device or a system, we would need to look at entropy generation in that device and look at ways to decrease the entropy generation so that it becomes more efficient. Unfortunately, entropy generation is practical and it cannot be avoided altogether, and that we will never have engineering devices in which entropy generation absolutely goes to zero. The reason is that most practical engineering applications involve constraints. What are those constraints? Some constraints involve space. For example, we don't have infinite space. So for example, if we wanted to exchange heat between two objects, if we had an infinitely large area, we could exchange heat at almost the same temperature, where the two objects are almost the same temperature. But we don't have infinite space or infinite area. We have constraints on area and space and volume. And so therefore, we need to have a finite temperature difference between the two objects between which we want to exchange energy, and that leads obviously to irreversibilities, as we will see in this example which I am about to do, right? So constraints on space, constraints on cost, constraints on volume, mass, etc., and constraints on speed. We cannot wait forever to achieve the objectives that we want to achieve when we build engineering systems. We want them to be achieved at a certain speed and as fast as possible. Unfortunately, speed and entropy generation go hand in hand together. So the faster something operates, the more entropy it is likely to generate, generally speaking. And so therefore, practical engineering devices will always have entropy generation, and unfortunately entropy generation corresponds to irreversibilities and therefore lack of or reduced performance compared to reversible devices operating between similar conditions. So these are some things that we need to remember about entropy. We'll do one small example to show how entropy generation works and how it degrades the performance. So assuming that we have two reservoirs, one at a temperature Th and another at a temperature TL, right? And assuming that we bring them into contact and there is some exchange of energy between the two reservoirs, and because this energy exchange happens to be because of a temperature difference, we can call it heat transfer. And so let us say that an amount of Q energy is transferred from the high temperature reservoir to the low temperature reservoir. We have two temperature reservoirs at two different temperatures, Th and TL, and they are brought into contact, so there is a heat transfer of the amount of Q between this reservoir at a higher temperature to the reservoir at a lower temperature, right? Now this seems to be a fairly common phenomena, two objects at different temperatures being brought into contact and heat being exchanged. But and we don't think much of it, but let us look at what is the change in entropy that either of these two reservoirs have, right? So so let's call this reservoir R1 and let's call this reservoir R2, right? And so we can calculate the change in entropy of the reservoir R1 as integral delta Q by T, right, over the process. And because this is a reservoir, a thermal energy reservoir, its temperature does not change, and I can pull that out of the integral, and I know that temperature is Th, so it must be 1 by Th times integral delta Q, and that is equal to minus Q by Th. Why minus Q? Because heat is being removed from that reservoir, and so therefore the change in entropy of reservoir 1 is minus Q by Th, Q being the energy transferred from the high temperature to the low temperature reservoir. Similarly, let me account for the change in entropy of R2, which is the low temperature reservoir, and that again I will write it as delta Q by T. Again, because this is a thermal energy reservoir, this temperature remains constant during the process, which means I can pull that out of the integral, and that I know is equal to 1 by TL. So this is integral delta Q, and this is equal to Q by TL, right? And so this Q and this Q are the same. However, here it's a negative Q because there is a decrease in the entropy of the reservoir R1, whereas there is an increase in the entropy for R2, right? And but the increase and the decrease are not numerically equal. Why? Because here I have minus Q by Th, and here I have Q by TL, and we know that Th and TL are not equal, and so therefore delta S R1 and delta S R2 are not the same. Even though we just brought them into contact, some energy went from one reservoir to the other. In this process itself, we have generated some entropy, right? So let us consider a system that consists of both of these reservoirs, and let's call this the combined system. So I can also write the change in entropy of the combined system, right, as, because this combined system does not have any other heat interaction with the rest of the surroundings or the universe, and no entropy is entering or leaving this combined system, I can write that the change in entropy of the combined system is the change in entropy of its constituents, and its constituents are only two, which is the two thermal energy reservoirs. So I can write it as a combination or an addition of the change in entropy of R1 and a change in entropy of R2. So I can write this as delta S R1 plus delta S R2. And so this I know is minus Q by TH, and this I know is Q by TL. So I can pull the Q out, and I can write 1 by TL minus 1 by TH. So delta S combined. Right, and so I also know that delta S combined is integral delta Q by T for the combined system plus S gen, right. So this is for the combined system. Now during this process, there is no energy that is entering or leaving the system, right. No heat escapes the system, no heat is added to the combined system, and so therefore delta Q by T for the combined system has got to be 0, right. So this delta S combined has to be equal to S gen. So which means that S gen in this particular example is equal to Q times 1 by TL minus 1 by TH. This shows that just bringing two bodies together which are at different temperatures causes entropy to be generated. And we now know that unless the two bodies are at different temperatures, we cannot have entropy, we cannot have heat transfer. So in order to have heat transfer, we need to generate entropy, right. So what we can do is minimize the temperature difference between the two bodies that are in contact, and thereby minimize the entropy generation, but we cannot make it 0, because if we try to make it 0, then we would not achieve any heat transfer and our engineering device would never work, right. So for it to work itself means that we need to generate some entropy, and this is an example that illustrates that point. One final thing to remember about entropy is how it's transferred from a system to its surroundings and from its surroundings to the system, right. One thing we note is that entropy is transferred to a system only when heat is transferred to the system, right. So we cannot have work transfer to the system does not transfer any entropy. Similarly, if the system does work on the surroundings, then the system is not transferring any entropy on the surroundings, which means that entropy transfer is associated with heat transfer, and that work transfer does not increase, that does not result in any entropy transfer, right. So entropy transfer is associated with work transfer. Right. So the heat, if the heat transfer to a system is, if to a closed system is 0, then there wouldn't be any entropy transfer to the system. Now the system can still generate entropy, so S gen can still be positive, but delta Q being positive, delta Q by T integral will be 0, and so therefore for a insulated or for a adiabatic system, we will have entropy transferred to the system as well as by the system will be 0. Right. So entropy transfer can only happen when there is heat transfer. Work transfer does not involve any transfer of entropy, right. And so or work interaction which means that if I need to look for all the entropy that is being transferred to the system as well as from the system to the surroundings, I only need to look at where heat is crossing the boundary of the system, and wherever it is, I need to record integral delta Q by T for that process for that system, and then I can account for entropy being transferred to the system as well as entropy being transferred from the system to the surroundings. And I need not look at wherever there are work interactions, because work interactions do not involve entropy transfers.